Okay, so guys, good morning. Today we have the talk by David Fernandez. So there's this PhD at Autonoma, working with Johannes Fest. I suppose I don't know how to pronounce it. Diego will talk about something, let's say, yeah, you can see, right? So it's some talk that it's of interest to everyone. So Diego, thank you so much for accepting the invitation. So yeah.
Well, first of all, thank you for inviting me to give this seminar here, and in particular to Tomas, who's not here, for reaching out and sending the invitation himself. So actually this project, I think it's very interesting. I hope you'll find so too. Tomas, I told these things to Tomas on a poster session about 2 weeks ago at Autonoma, and he seemed to be very interested. So well, I hope you share that interest, at least after the talk. So, well, to begin with, I guess we couldn't really start any better with a very bold and strong claim. I'm going to do my best to try to justify it and hopefully convince you that that is not as strong a claim as it seems, and it actually makes some sense. So let us first revisit the interaction regimes between light and matter. We generally consider that we have photons and atoms. They interact with each other, and in free space, this interaction is limited to the weak coupling regime, meaning that we basically have a small energy shift of the levels, called the Lamb shift, and the energy levels become wide, so they have like spontaneous emission. Nothing more. Everything is well described within the weak coupling regime, perturbation theory. This is well-known stuff. Now, people became interested in trying to increase the coupling strength. And to do that, they realized that by putting atoms inside cavities, we could increase the coupling strength because the photons now were going back and forth between the mirrors in the cavity. So basically interacting many times, if you want to see it that way, with the atom. And this leads to the following regime. Once you crank up the coupling strength enough that it becomes larger than the losses of both systems of the cavity, or the photons and the atom, you start to see a hybridization of states, a coherent energy exchange between matter excitations and photon excitations. These are called polaritons. This is all very well known, very simple, easy, James Cummings stuff. And this is called the strong coupling regime, where we have coherent energy excitation between our degrees of freedom. Now, if we try to crank up the coupling strength even more, we can reach what's called the ultrastrong coupling regime, which is characterized by the coupling strength becoming a sizable fraction of the bare energy difference between the states. This ultra-strong coupling regime has many features that one could look at. One of them is that we start mixing states with different excitation numbers. In the previous case, we only mixed states within the first excitation subspace. Now we mix states with different kinds of different numbers of excitations. And it has, well, many potential promising applications that we're not here really to discuss. Okay, so let me now give a few brushes about how we describe these systems theoretically. We use a theory called non-relativistic QED. Non-relativistic because we work with atoms or molecules, so we don't need to describe them moving very fast in general. And this is like the Hamiltonian you arrive at when you read Cohen-Tanucci or any other quantum optics, quantum electrodynamics book. Basically, you have the charges, the fields, and which are the photons and their interaction. This is called the minimal coupling Hamiltonian because it comes from expanding the P minus QA in the charges And this is all very well known. There are many equivalent formulations. You can do any number of unitary canonical transformations upon this Hamiltonian and reach different looking descriptions. But the physics is here, and this is the Hamiltonian that in some sense I like the most to start theoretical discussions, because it very clearly separates the degrees of freedom of the charges and the photons. In some sense, the photons are here and only here, and those can be seen as the excitations of the transverse electromagnetic fields. Fine, this is all very well-known stuff. The problem with this Hamiltonian is that it has way too many degrees of freedom. So what we do is try to find simplified models, like extracting one single mode of the electromagnetic field that carries most of the interaction strength, or truncating the Hilbert space of the charges and the photons as well. But these simplified models come at a cost. Like it's been reported that you can break gauge invariance. The role of some of these terms can be unclear depending on which initial of these many equivalent formulations you start from. So there are many things to consider that are sometimes lost when you just think about the simplified model. So in general, what we have is a theory of charges and photons. And the charges, I'm going to do something that I think makes a lot of sense. I'm going to separate the charges in the atoms or emitters, and the structures, which can be like the cavity mirrors, anything just like that. And then the photons. And we have this three-partite system interacting all terms, all with all. And like the photon and atom, the structure and the atom interact with the photons via this P dot A term, and then the structure and the atom interact with each other via direct Coulomb charge-charge interactions. This is the full picture. Now, the simplified models come in when you want to describe a particular configuration, like for example, a Fabry-Perot microcavity. Here you have the photon going back and forth, the atom, you have your vector potential, which is confined, that gives you like a discrete Fabry-Perot resonances, which are your new modes. And basically in this description, usually people neglect the direct interaction between the mirrors and the atom. This is well justified because the mirrors are very far away. And so the atom basically doesn't see them. It only sees them through the photons that come back in some way, but not directly the charges. Basically, this part of the Hamiltonian or the interaction Hamiltonian is the one that dominates. And if you want to reach ultrastrong coupling with this kind of configuration, you need to resort to collective effects. You cannot have ultrastrong coupling in a Fabry-Perot microcavity with one single atom. You need to have like an extended many-body system, electron gas, something like that. The other setup that I'm going to be discussing a lot is this one, in which you basically reach ultrastrong coupling through sub-wavelength confinement of the light. Basically, in this kind of configuration, one could at least expect that because the atom is now much, much closer to the mirrors, or in this case, the spheres, it will start to see the charges and interact via Coulomb interactions with them. In this case, again, the sub-wavelength confinement of the electromagnetic field is what leads to the ultrastrong coupling regime.
One question.
Yes.
If you're in the ultrastrong coupling, what argument you use for neglecting the term A squared when?
Okay, that will become probably more clear in the second part of this talk, in which we actually solve a system analytically and see that it doesn't play a role. But basically what we're claiming is that here in this kind of setup, photons, well, here what I just said is that this part of the interaction, this Coulomb interaction, should be important. What I'm now going to try to prove is that the photons themselves can be completely neglected. Like all the physics in here is electrostatic physics. That's what I'm going to claim. And if it's all electrostatic physics, the A squared and the P dot A don't matter, I mean, they can matter insofar as they provide a free space lamp shift, but that can be renormalized away. That's more or less the argument, or part of the argument. So let me try to convince you now that it is indeed going to be electrostatic driven interactions, the one that play a role in reaching ultrastrong coupling. Yeah, so the full Hamiltonian contains everything, of course. The question is which subpart or which terms of the Hamiltonian we want to keep in order to describe ultrastrong coupling. And of course, if you reach ultrastrong coupling through the P dot A, then the A squared plays a big role. If you don't reach ultrastrong coupling through the P dot A, but through the Coulomb interactions, then the A squared doesn't play any role that it doesn't play in free space, so to say. And one of the examples of the things that people think about when they're discussing ultrastrong coupling and these things is that, well, first, you can shift your description from the minimal coupling Hamiltonian that I showed before to this multipolar coupling with the powers in Alfvén transformation. This is well-known stuff, textbook stuff by now, although there was like a recent controversy of whether this thing was correct or not, but it was finally shown that, yeah, it's fine, it's consistent. And you'll see that we have the charged Hamiltonian, which looks the same as before, but now it contains this polarization self-energy or dipole self-energy. It's a term that basically arises, it's like the equivalent of the A squared when you go into this new picture. Like before, the canonical momentum of the field was E, now it's the displacement field. And as a consequence, you get this extra P squared. Whereas in the charges, the canonical momentum was before the velocity plus QA, and that's why you get the A squared. So this is E minus P. So when you expand the square, you cancel that, but you cannot actually do it because D is the canonical momentum, the variable you want to describe your dynamics with. But there are many things about this polarization of self-energy, but the thing that I want to transmit is that people are discussing whether it's important or not in setups that concern, for example, polaritonic chemistry, ab initio simulations, things like that. And their argument is that you basically reach somehow a single mode description for your electromagnetic field. And then it turns out that the size of this term depends directly on the square of the coupling strength to that mode. So that G square. So obviously, if you're in the ultrastrong coupling regime, you would expect a large dipole self-energy correction. This is what some people are claiming, and what we think they're claiming in some way incorrectly in a particular context. And it all goes back again to the same question: what if the ultrastrong coupling is due to the Coulomb interactions rather than the P dot A? And if that is the case, if that were the case, then basically we only need that part of the Hamiltonian, again, splitting the charges between the structure, the mirrors, and the atoms. And then we can basically extract some of the multipolar resonances of our structure, like the dipolar resonance of a sphere, and that corresponds to a single mode to some degree, and we can reach ultrastrong coupling with it. And there is no polarization self-energy here, which is more or less like there's no A squared term here playing a role. The A squared and the P squared are not the same thing, but they originate from the same problem, in some sense, from the fact that photons exist. But again, this polarization self-energy just doesn't know anything about the charges or the interaction between both charge centers, the spheres, the structures, and the emitters. So this has led to some debate. And now I'm going to outline the rest of the talk, basically, because some people have been applying this kind of description with P dot A's and A squareds to this kind of setup, and there are some references there. What we're going to do is basically find first a fundamental bound to the charge photon coupling strength. And then with that bound, we will show that you cannot actually reach ultrastrong coupling with photons and single emitters. And then there's the second part of the talk, do a particular analytical example to show that all of this is more or less the case, that I'm not making anything up. Okay, so yeah, that's the interaction Hamiltonian, the interaction with the longitudinal or Coulomb fields between the atom and the sphere, and then the P dot A. From the perspective of the atom, everything. We're going to forget about this term for a little bit because we're interested in putting a bound to the photon part only. And then we're going to expand A in terms of photon modes. These modes are creation and annihilation operators. This is nothing too surprising. And then we're going to write everything in terms of the dipole moment of the emitter with this relation that exists between P, matrix elements of P and matrix elements of R. And then what we're going to do is take this part of the Hamiltonian, which are harmonic oscillators, and diagonalize that together with the harmonic oscillators that describe the resonances of this sphere in particular, or any kind of structure. And by diagonalizing them, we reach the new polaritonic modes, which again are harmonic oscillators, and the Hamiltonian looks the same as before, but now this coupling strength is different. Before we had like the free space coupling strength to photons, pure photons, and now we have a new coupling strength, which is to photons and the polarization field of this thing. And yeah, basically what I just said. And just for convenience, we're going to define this quantity, the spectral density, which is, you can see it as taking all of the modes at a particular frequency and combining them to find like the bright one that's coupled to the emitter. The rest of them are orthogonal and uncoupled to the emitter. So that would be the final A or the final B. And the spectral density, combine them all here. And then it has the coupling strength squared inside. Okay, this is just for convenience because it's easier for us to work with the spectral density. Now with this setup, which is like basic stuff, I'm going to show how we can put a bound to the photon matter coupling strength. So the first thing is we're going to use this transparency constraint, which means that for sufficiently high frequencies, the sphere or the structure becomes transparent. This is normal. You can also see it like the permittivity goes to 1 at sufficiently high frequencies. Basically, the charges inside don't have time to respond to the very high frequency oscillations of the fields. And then the other constraint that we're going to use is that there is a Kramer's chronic sum rule, which, as all Kramer's chronic rules, comes from causality ultimately, which is like this, and basically adds another constraint to the spectral density. So now we are going to use these two. And in particular, we're going to apply them to a imaginary scenario of a perfect transverse cavity. Perfect transverse cavity being one that takes all of the coupling strength and gives me just one single peak resonance. And we're going to assume that it's infinitely thin as well, so that we really have a single mode. But we can't just do something like that. We need to add free space at sufficiently high frequencies. So we add, for some high frequency lambda, we add like this step function. Great. And then if you plug this one into the sum rule, like the integral that I showed before, you reach that the coupling strength, this G, is basically this thing, which makes sense because the more interaction strength that I managed to put in, so the larger this lambda is, the larger G becomes as well. And this is a bound already on the coupling strength. If we have a material that can respond up to a certain frequency, then by making a perfect cavity with that material, we can, in the best case scenario, confine all of the coupling into, or concentrate all of the coupling into one single mode with this coupling strength. That's more or less the gist of the argument. Now, yeah, summarized by this sentence. Now the thing is, we can apply this straightforwardly to ultrastrong coupling with single emitters, because well, this is just another way of rewriting it in terms of the single mode that corresponds to it. That thing there is the coupling strength. G is what I just showed, and D is the dipole moment of the emitter, which can be also constrained with the Thomas-Reichenkuhn-Sum rule, which for small emitters dominated by single or few electron physics gives me a constraint on the absolute value of D, over the magnitude of the dipole moment. Putting all of these things together, we reach this equation, which is already the coupling strength normalized by the frequency, transition frequency. So the parameter that will tell you whether you're in those ultrastrong coupling regime or not, which is just a bunch of fundamental constants and lambda, your transparency window, if you want. And then if you want this to become like 10 to the minus 1, so 10%, you need lambda to be of the order of 2 mega electron volts. That's really high, which means that there is no material that can, like if you imagine photons are cheap, there's no shepherd that can put so many photons inside the cavity if you want. So that's why you cannot reach ultrastrong coupling with photons, because you cannot confine the coupling enough. There is no material that still responds at 2 mega electron volts, or no material that you would use to build a cavity anyways. This is it. So if single emitter ultrastrong coupling cannot come from photons, where does it come from? Well, as I already hinted at, it must come from the longitudinal interaction, the Coulomb interaction between the charges in the mirrors or the spheres in a plasmonic nano gap and the emitter.
Sorry,
Yes.
I'm getting a bit lost with this capital lambda. So this is the way you write it. It looks to me like an ultraviolet cutoff or something like this.
Yeah, that's a bit unfortunate. It's not a
yeah.
cutoff.
It's
not really a cutoff.
But you have some, like, you are free to choose any lambda, capital lambda that satisfies. Basically, capital lambda is the energy above which you can consider that there is no interaction between the.
It's the energy beyond which.
Because it's so high that the electromagnetic field is like free, right?
It doesn't really have to do with the emitter itself. It has to do with the response of the mirrors that build your cavity. Beyond some frequency, your cavity becomes transparent.
Yes.
Which means that it does not interact with those photonic modes. It interacts with the photonic modes of the resonances it creates, but the photon modes that just go through it for sufficiently high frequencies, it doesn't interact with those. What we're saying is that the emitter interacts with those photon modes exactly equally as it would in free space with those very high frequency modes.
Okay.
And lambda tells you where that frequency range starts. So basically, this spectral density tells you how the emitter couples to the electromagnetic modes. What we're saying is that the cavity allows or makes the photons or confines the photons in a way that many of them just give me just one single resonance, and then the cavity is not able to affect the high energy modes. So the high energy modes still interact with the emitter in the exact same way as they would do in free space. That's the.
What's the problem with this number being as large as you want? Because it looks to me like it sets up a kind of upper bound, or like any energy beyond that is not confined by the cavity, or it's not. Well, this can be. What's the problem with this not being as large as you want? This is what I don't understand.
So the thing, okay, we would need it to be larger than that.
Yes.
Which means that we would need the cavity to affect the photons of frequencies larger than that. So we would need the cavity to interact with the photons that have more energy than 2 mega electron volts.
No, but it was the other way around, right? It was like the modes that have larger energy than that are the ones not affected.
Yes, exactly. But what I'm saying is, if you want to reach the like the larger you put your lambda, the larger the coupling strength becomes. So if you want to reach ultrastrong coupling, it turns out that you need to put lambda larger than 2 mega electron volts. So you need a material that will interact with the photons at least up to that frequency. Beyond that, you don't care, and beyond that, it can again become free space. The problem is that no material interacts with photons in the way you would want it to, at least, to confine in a cavity for frequencies that are already much, much lower than 2 mega electron volts. So the problem is that this number is way too big for real materials. Maybe I just repeated what I said before, and it's not clear.
No, it's fine. I mean, it's maybe that I would have to think about it, but I'm not very much into the field, so that's why maybe I'm not getting the. But I think it's an interesting.
So what's the criteria how to get to 2 mega electron volts? In the sense of like the number you put in, what do you call ultra strong?
The fact like this quotient has to be like 10%.
10, okay, 10%.
And it only depends on lambda.
Yeah.
So basically just evaluating all the constants, it comes out of the theory.
So you say 10% of that.
Yeah, I mean, it can be
Of course,
5% or
yeah.
it doesn't change that
And
very
it's
much.
quadratic. Sorry, in that square root.
Yes.
So even if you take something mildly different, it's not mildly different.
Yes, exactly.
And this is related to somehow the lattice spacing of the materials that form the cavity, or so the inverse of that is roughly or not.
To be honest, I had never really thought about it that way, since that I've always thought of materials from like more macroscopic electrodynamics kind of way, like a continuous medium, things like that. So I'm not sure what the role of the actual lattice spacing would be. I can't really answer that.
Yeah, so basically you're just saying like there is no material that has this that fulfills this bound, but there could be some metamaterial or something like this that you know, as Lucas says, something made out of I don't know, some structure, some lattice or whatever. It could have, you know.
Yeah, for instance, superconducting circuits where we can have seen ultra-strong coupling, maybe in that case the lambda is larger.
Yeah, but what I'm not sure about is like, and maybe you'll correct me in this, superconducting circuits are in principle within or are described within this Hamiltonian that I just put before, just not in a very straightforward way, right? There's nothing else that's not there.
It's not in free space. It's not.
No, yeah, of course it's not in free space, but this atom close to a cavity is also not in free space. The thing is, my bet would be that in those superconducting circuits that they reach ultrastrong coupling, the dominant interaction would be in principle traceable back to Coulomb interactions. And I've really probably read like one paper on superconducting circuits and just skimmed through it. So I really don't know how much of the analogy holds in here and there. So maybe I'm saying something that is really stupid, but that would be my guess.
Okay. That could also be that with the other material you can build. In your case, the material is like a cavity in free space. You know?
Well, it doesn't really need to be a cavity. It could be. I'm actually going to show you an example next with a sphere, a plasmonic sphere. Without real confinement, but with subwavelength. Yeah, I mean, what do you call confining? This field is. But
then are you saying that okay, these experiments are actually reaching the ultrasound coupling, but
yeah,
the
I mean,
explanation they give is not fully.
I mean, the experiments, I have no problem with experiments. We weren't really thinking about superconducting circuits when we first started started thinking about this project. And we were thinking about some people who have been functionalizing some plasmonic particles and then basically putting a molecule very close to it and reaching ultra-strong coupling. And it turns out that some theoretical people have been claiming that, not claiming, but implicitly assuming that that ultra-strong coupling regime could be described with the same physics they would use for a Fabry-Perot cavity, which is more or less the initial motivation that I wanted to try to convey, that different situations call for different approximate Hamiltonians. In one of them, some terms appear that are gauge dependent, and all sorts of complicated stuff. In some other situations, the Hamiltonian that's called for doesn't really include all those terms. Yeah, that's more or less the claim.
And so when we sequence, the photons are not really photons, they're kind of plasmons.
Yeah.
Material.
So they would be, in a sense, the polaritons that I called here, like the mixed excitations. It doesn't need to be polaritons, it could be plasma polaritons, could be phonon polaritons. But those excitations are of a mixed nature,
yeah,
not really photons. And the thing is, what I'm going to show you next is that you can write this transverse interaction. So the interaction with the photons, you can write it in terms of the polaritons, but the interaction with the structures, charges, you can also write it in terms of the polaritons. So everything from the perspective of the emitter is coupling to polaritons, but there are two sources of coupling. The part that comes originally from the photons and the part that comes originally from the charges in the structure. And the idea is that one of them dominates over the other by a huge margin. Mm-hmm. So my guess would be that in superconducting circuits, it's the same.
It could be that the lambda that you reach is larger.
But I don't know how you would reach, like 2 mega electron volts is huge. Also, maybe in superconducting circuits, the emitter is not an atom. Exactly. So the dipole moment also increases.
Yeah, and the frequency is lower.
And the frequencies are lower, exactly. But then, I mean, all of these things are in principle for atoms or small molecules, which are interesting, I guess, but not necessary for any kind of emitter one might consider.
So,
not that I know
for example, like if you have many emitters and collective modes, this argument doesn't work anymore.
This doesn't quite work because the dipole moment of those collective excitations, again, you can say that it follows some Thomas Ajekun sum, but this n here is huge.
Okay.
So, and that, for example, we have strong coupling between the photon and the structure because, I mean, we have plasma polaritons here, and those are like, we see them. We're not making them up. And those are like the collective excitations of many charges. So that's also something to take into account. Okay. Okay, well, if I may continue, we have like a corollary. It's just what I said before, the polarization self-energy in these kinds of single emitter in a plasmonic nano gap. Well, the polarization self-energy doesn't really play a role. You would need to use that kind of description because that's the one that comes from Coulomb interactions, which are the ones that I claim dominate here. And now, this is my favorite part of the talk, because the one that I did on my own, for the most part, the other part was much more ideas of my supervisors that we sort of developed. But this is like an analytical example, almost academic, that where you can actually see everything that I've been saying in detail. And what we're going to consider is a plasmonic sphere, which is basically made of a positively charged sphere and a negative one. that's oscillating back and forth. So this is our main approximation. We have replaced a sphere with all its complexity by this very simple model, which is supposed to represent very well the dipolar resonance of a plasmonic particle. Well, it's not supposed, we know that it does, and we've checked that it does. And interestingly, this frequency that appears here, or this interaction, this quadratic interaction, comes from solving the Coulomb interaction, basically, integrals. And that plasma frequency that appears there is the plasma frequency you would expect for a small sphere with a lossless root permittivity, blah, blah. So everything, what I'm trying to convey is that everything works out fine. What I'm going to do now is diagonalize this thing. What you can see is we have a harmonic oscillator there. The electric field is many harmonic oscillators. So it's basically diagonalizing oscillators and seeing what happens. Okay, this is the Hamiltonian. And then we have the atom, the sphere, the fields, and the interaction between the atom and the sphere. We're going to do the long wavelength approximation for simplicity to get like an analytical expression. So this is proportional to B and proportional to the displacement of the sphere and proportional to the dipole moment of the emitter, blah, blah, blah. Okay, and the modes, for the modes, we are going to use the spherical wave basis, which is not the prettiest one, but it has a nice advantage, which is that due to the symmetry of the system, only the L1, M0, and transverse magnetic modes couple to the sphere. So that is a big simplification. And now, I guess we already spent quite some time. So these are like the steps, something you should try to do on your own because it really makes you a better person. No more reason than that. Basically, that's the procedure we're using. It's a funnel diagonalization. Those are standard things and not very interesting from the fundamental point of view. The key takeaway is we managed to do them analytically, all of the integrals, all of the everything. And now we can explicitly solve for the variables in our model in terms of the new polaritonic eigenmodes. So we can express the atomic interaction with the photons and with the sphere in terms of these polaritons. So the first one becomes this big thing here. The second one becomes this big thing here. This contains like the free space coupling strength. This with this final coefficient, blah, 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 contains like the coupling to the new polaritonic modes and the transverse part of it. Whereas this one is like the longitudinal part of the coupling to those polaritonic modes. And yeah, again, this integral can also be done analytically, but it's not very nice. And this is what we obtained. There are many plots here. I'm going to be going one by one. The first one is the spectral density, so the coupling strength basically associated to the longitudinal interactions and the transverse interactions. And you can see that with the scale, one is much larger than the other. This one reaches 10 to the 2, this one reaches maybe 10 to the -4. And at this particular value of the sphere's radius, you can see the longitudinal, the transverse, and the free space one. You can see that the free space one and the transverse one are very close to each other, except for a very narrow region with the final peak and the final dip. And the other one, due to the Coulomb interaction, looks like a Lorentzian. It makes sense because we have a single harmonic mode, which is slightly broadened because it interacts with a continuum of photons. So it's harmonic, like a Lorentzian, basically. And what I was saying now makes more sense. The interaction is dominated by the Coulomb interactions rather than the P dot A. This other plot tries to show that in a more, like in a map. What we're calling longitudinality basically is the ratio between the average longitudinal and the average transverse spectral densities within some range. And these lines here show you like the fraction of the coupling strength divided by the frequency. So here to reach ultra-strong coupling and beyond for these parameters. These parameters are not really necessarily realistic. Again, it's almost an academic exercise of diagonalization and wrist strengthening. But again, it goes to show that when you reach ultra-strong coupling, you are in a regime where the interaction is primarily longitudinal. But if you go further away, like 5%, whatever percent, it's still 10 to the 5 times larger, the longitudinal compared to the transverse interaction. And the last plot doesn't really make sense to discuss it much here, unless you're interested. So let me finish with some conclusions. We found this bound, which we were proud, and it depends on where your material must stop responding to the electromagnetic field. We applied it to the ultrasound coupling regime, and we saw that you could not really reach it in a single mode emitter configuration sub-wavelength, Fabry-Perot kind of setup. And then we explicitly saw in this analytical example that Coulomb interactions, so the longitudinal ones, really dominate by a mile compared to the other one. And yeah, this is all I had. So if you have any more questions, please ask them. Feel free.
Sorry for the long question, but so if I understand correctly, however, in this presentation you have shown that for these type of approximations, the ultra-strong coupling would not be possible because of the materials needed currently don't exist. But as far as I'm aware, it has been observed in systems approaching in lab systems, like an experimental lab.
Mm-hmm.
So what you're implying is that the models they are using to understand those experiments are not correct, because according to this presentation, the approximations they use implicitly force this constraint that it's not feasible.
Yeah, in some sense, I guess what we're saying is what we're claiming. What we're saying, let me rephrase it, is that experiments have reached ultra-strong coupling. That's fine. Some people have tried to describe those experiments in a way that involves this A vector potential, so photons. What we're claiming is that in some of those setups, that's not a correct description. So which brings the added benefit that you don't need to deal with the A squared term or gauge invariance, because nothing is gauge dependent in the Coulomb interaction. It's just the Coulomb interaction between charges. It's the longitudinal part of the electric field, which is a gauge invariant quantity. So basically you remove many problems of the equation, simplify the model, and do things more correctly, I guess.
This comment about the gauge invariant part, I guess this is because, okay, so if I understand correctly, the models they're using are not completely correct because of this implication that you showed, but I guess the other comment that you made about the gauge invariant part, that points to a way to how to model the systems, or like in this description you've done, okay, it puts a limit to the description, but it also points to a other possible way of approaching the system, or it's just like okay, here, it's not a way to
so the idea is, so we're not really thinking too much about what happens, gauge invariance and blah, 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 because what we're claiming is that the interaction or the terms that drive the interaction are gauge invariant themselves. It's not the A, or better, it's not the longitudinal part of A, because you can gauge away that thing and basically just rewrite all of the longitudinal part of your interactions in terms of E longitudinal. So if that's the only thing that appears in your equations, then your equations are manifestly gauge invariant.
What is the typical lambda of the material of a standard mirror, you know?
Of a standard mirror, I wouldn't know. But for example, in plasmonic particles, even without reaching that such high regimes, like the dipole excitation is at a few electron volts, then you have more higher multipolar excitations, but those, like the frequency of those reaches a maximum, and then you end up having like the so-called pseudo mode at about maybe 6-7 electron volts, a few tens of electron volts maybe. So I wouldn't know about any material that you can think of, like what's the particular lambda. The frequency that metals respond to light with are, I would say, typically not more than, say, 100 eV. And I would say that's already a lot.
And maybe that's for optical photon, but for other frequencies, maybe it's already in circuits. Maybe there is that like materials like that where this is strong.
Yeah, but the thing is, with the limit, it's there. Okay, sure. This limit depends on the frequency of your excitation. So if the frequency is lower, that becomes lower as well. But the thing is, or the lambda effectively acts larger. But the thing is, the full quotient here, this full quotient doesn't depend anymore on omega, on where the mode appears.
It's because the kind of spectral function you would choose.
No, I mean, the only thing you could say we're assuming is that the mode that we create, the cavity mode we create, is on resonance with the atom, which is like, I mean, you would want that.
Yeah, but in the resonance of the atoms, which is different than the resonance of a smaller frequency.
Yeah, but okay, so the frequency of the emitter, if your emitter is at microwave or whatever, then put the resonance there, fine, everything carries that. But the thing is, for the systems we're interested in, like small emitters dominated by singular few electron physics, this dipole moment carries a dependence on the frequency of the transition. And that dependence added to this one, like what you want to reach ultrastrong coupling, this quotient, kills off any omega dependence in here. So maybe the thing is, if your superconducting circuit experiment has or is another kind of emitter, then all of this may have a caveat because this n might not be 1 or close to 1.
Yeah, exactly.
So, and this is again what I was trying to say at some point. This idea came to us because some people were trying to model some experiments in a wrong way, assuming that photons played a role, not taking into account something that has been known in nanophotonics for many years, which is the quasi-static approximation. Like all of what I've just told you, some people from nanophotonics already knew that, okay, quasi-statics dominates. So what? So if you're in a regime or in a scenario, experimental setup in which quasi-statics doesn't quite dominate or not as much as you would want it to, then photons play a role and the A is there, the A squared will do something as well, I guess. That's more or less the claim. So if that's the case for superconducting circuits, which I'm no expert on, by no means, then yeah, you would have to.
Yeah, so use superconducting gives the kind of interaction difference, a capacitive Coulomb interaction.
Sorry, what kappa?
A capacitive interaction between superconducting qubits, you consider the capacitive interaction.
Capacity.
Yeah,
Okay.
so
Yeah, but still you can have a dipole interaction. In that case, by dipoles are larger.
Yeah, but a dipole-dipole interaction in this case would be like the Coulomb interaction. In this simple model that I show, it's like the interaction between the dipole of the sphere and the dipole of the atom. Just
No, but that
in full glory.
with photons in a way that in a transmission line.
Uh-huh.
It's possible to get strong coupling of photons and photons which are actually plasmons coupled to qubits.
Well, my guess would be yes, but the thing is, those, if the qubit is small and you reach ultra-strong coupling, then according to this, that means that the qubit is interacting with the longitudinal part of the electric field produced by the plasmon, not with the transverse part.
Yeah, I don't think so, because the transfer part is where you put the photons, when you quantize the field.
Mhm.
This you can do in working circuits and you can quantize the field with photons. That's what- I think your claim is fine, but for a specific type of experiment, not for all,
Mhm.
not all for all systems.
Yeah, yeah. I mean, we even, like, we're no experts on superconducting circuits, so we try to avoid discussing them at length. But here we say that for collective effects, like the first times people saw ultra-strong coupling in cavity QED like setups was with inter-subband polaritons and things like that, like extended many body condensed matter systems. And for those, yeah, fine, photons. But thing is, people are trying to extend that description without thinking too much to systems where you can't. So that's more or less that.
One thing I would like to understand, because in atomic physics, normally everything is very clean, and the first principle calculations, and have these debates somehow because. But I mean, so the kind of situation that you have, you say that people do experiments, and isn't it possible to do a first principle description that settles down this kind of discussions, like saying this is my Hamiltonian, I solve it, and that's the how is it, can you comment a little bit about the field, how
Okay,
how is the status of experiments and whether you can describe them or not?
So as far as I know, there have been some experiments reporting ultrastrong coupling with a single molecule very close to a plasmonic gap. And there are like two schools of theoreticians, some who have more in-depth background in nanophotonics, who know that in those situations, there is no A squared term because it's the interaction between the longitudinal part of the electric field due to the plasmon and the molecule. They know that. And
so the point is the difference is in the effective description of the
yes.
plasmas. Oh, I guess.
Yeah, somehow. And that's well known. And the thing is, okay, now I'm going to point my finger to some theoretical groups. There are some groups that shall remain unnamed who have developed an ab initio theory for polaritonic chemistry. So basically their system of interest is a molecule or a bunch of molecules inside of a cavity, and then they try to describe that ab initio and see some effects. And what they do is they start from a Hamiltonian, which is basically the one that I showed at the beginning. And then they go to the multipolar coupling picture, everything's fine. And then they select one mode and say that that's the one ultra strongly coupled to your matter. And okay, fine. But then the next claim, which is incorrect, is that they say, since now we're seeing experiments doing stuff with plasmonic nanogaps, and they are reaching these very high values of the coupling strength, we are just going to put those numbers into our model. But our model comes from assuming that the interaction is mediated by something that would be a Fabry-Perot cavity resonance, not the interaction, the Coulomb interaction. And as a result of that description, they reach dipole self-energy term, so an extra additional quadratic potential to the molecules, that's huge. And that doesn't make any sense. And the thing is that some people in the quantum chemistry field who maybe don't have such a strong background on electromagnetism are now switching or starting to do experiments in theory for ultra strongly coupled systems. And they are following those references because those are the references that are in the literature that address the chemistry community. So what we're trying to say, or one of the messages we want to transmit, is to those in the chemistry community, don't pay too much attention to these guys without consulting with another expert on electromagnetism. Because maybe what they're doing is fine in some context, then they write some sentence about it in the paper, which claims that it's appropriate for other contexts, but it's not. So that's more or less the origin of this whole idea by Johannes.
That's interesting.
Okay.
Thank you.
Thank you.